On behalf of the director of the Ramón Areces.
En nombre del director de la Fundación Ramón Areces, quisiera dar la bienvenida a esta fundación y a esta conferencia. Déjenme presentarme. Mi nombre es Mario Santín. Soy profesor de Económicas en la Universidad Complutense de Madrid. Y yo también estoy encargado de colaborar con la Fundación en algunas de las actividades que se organizan o se patrocinan por la Fundación Ramón Areces. Este evento estará en inglés. Sin embargo, ya que una de las prioridades de la Fundación es fomentar el uso del idioma español en la ciencia, voy a hacer parte de esta presentación en español. First of all, me oigo en inglés, ¿eh?
Perdón.
Bueno,
Perdón.
que me oigo en inglés, está algo mal aquí. Muchas gracias por dar esta charla.
En segundo lugar, quisiera agradecer al profesor Ramón López de Mántaras su papel de hoy como moderador de esta conferencia. El profesor
López de Mántaras is a professor of research from the CSIC in the Institute of Research in Artificial Intelligence and one of the maximum experts in this field, in which there are more than 300 scientific publications and several papers. I'm not going to go into detail because to start talking about the CV would take us the whole afternoon. Thirdly, in order for those of you who don't know the goals of the Ramón Areces Foundation, let me tell you that it's very easy to summarize what the foundation does. It's just a goal that is to promote the excellence of science in Spain. For that, the foundation has different calls. Among them, I would like to point out the call for grants of postgrad abroad that allows the best Spanish students to study in the best universities worldwide, the program of pre-doctor and postdoc programs, aids, and the research projects for people under the age of 40. The foundation has as well several strategic alliances with some of the best institutions worldwide, as MIT or London School of Economics. And finally, the Ramón Areces Foundation is achieving many conferences as this one, where excellence of science is in contact with the civil society so that they can know firsthand the scientific progress from those who really are proposing them. Y finalmente, ayer, cuando estaba preparando esta charla y estaba llegando al final de esta charla, pedí a ChatGPT por centros motivacionales para terminar esta introducción relacionada con la charla de la conferencia. ChatGPT me ha contestado con las siguientes ideas. En nuestra petición de la inteligencia artificial verdadera, por curiosidad y impulsada por el deseo de hacer un impacto importante y duradero en el mundo. Muchas gracias y estamos deseosos de empezar a escuchar esta conferencia. Y el profesor tiene la palabra. Buenas tardes, bienvenidos a todos. No he utilizado ChatGPT. No le he preguntado a ChatGPT que me escribiera sobre la presentación del profesor Wooldridge, aunque lo hubiese podido hacer, pero estoy bastante seguro que hubiese tenido muchas, lo que tendría alucinaciones o cosas o curiosas hubiesen ocurrido entonces. Pero Mike Wooldridge es profesor de Inteligencia Artificial en Oxford, en la universidad, donde ha estado como jefe del Departamento en Ciencias Computacionales desde 2014 hasta 2021. También es director de IA para el Instituto Alan Turing en Londres. Ha recibido múltiples premios por tanto investigación como educación, incluyendo la medalla Lovelace 2020 de la Sociedad Británica de Informática. Esto es el premio líder para los científicos computacionales en el Reino Unido. En 2021, él recibió el mejor premio de las personas en inteligencia artificial y el fellowship también en lo mismo. Desde el año Desde 2014 a 2016 era presidente de la Asociación Europea de Inteligencia Artificial y desde 2015 a 2017 presidente de las conferencias conjuntas sobre inteligencia artificial. Actualmente está liderando este campo la revista líder de la IA, establecida desde hace ya más de 15 años. Como autor ha escrito cientos de artículos científicos y 9 libros que han sido traducidos muchas veces. Estos libros incluyen 3 libros populares de ciencias. Uno de ellos es el Lady Bird Expert Guide para la inteligencia artificial del Penguin, El camino a las máquinas conscientes de Pelican, es el pueblo que lo ha publicado, y más recientemente, en 2021 creo que fue, una breve historia de la inteligencia artificial. Mike da charlas frecuentemente sobre inteligencia artificial, incluyendo el Festival Hey y el The Sciences, y se le ha entrevistado con frecuencia por los medios. Y ahora, muy importante, este aspecto, en mi opinión, que era uno de los
of Mike's first-class, world-class scientist is that in December 2023, so very recently, he gave the 2023 Royal Institution Christmas Lecture. This was the 199th year of this series of lectures that were created by Michael Faraday. To give you an idea of the importance of these lectures, let me mention a few, just a very few, notable lecturers. Michael Faraday itself, obviously, Desmond Morris, Sir David Attenborough, Carl Sagan, Richard Dawkins, Ian Stewart, and Marcus de Satoy. These lectures of the Royal Institution, the Christmas lectures, present scientific subjects to a general public, to the general audience. Now, in today's lecture, Professor Wooldridge addresses questions such as, what is artificial intelligence? Or can a machine have understanding? There is indeed quite a lot of confusion, not only among the general public, but also among AI practitioners about what is AI, and if really machines can understand or do understand anything. In my opinion, one of the reasons is our tendency towards anthropomorphization, that's a difficult word, of AI, particularly with the most recent trends in AI, the so-called generative AI, based on extremely large models that require enormous amounts of training data and enormous amount of computing power. Many AI scientists believe that the bigger the models, the more intelligence or the more comprehension has the AIs. Others, including myself, and I think Mike too, believe that generative AI is not the right path towards a more general AI and a true understanding. That is going beyond what Daniel Dennett says, competence without understanding, and competence without comprehension. If you want to go farther than that, I don't think that the recent trends of generative AI are the right way. Actually, maybe they are an off-ramp. In today's talk, then, Professor Wooldridge will enlighten us on these ideas. Mike, the floor is yours, please. Let me join me in applauding Mike.
Thank you, Ramon, for the slightly over-generous introduction. It's going to be a little bit difficult to live up to that introduction. What Ramon didn't say is that he's an old friend, and his institute, the CSIC, Center for Artificial Intelligence at University Autónoma de Barcelona, have been a long-time collaborator with. So it's wonderful to see friends in the audience and other friends from Madrid going back a long way. So, artificial intelligence. I've been an artificial intelligence researcher for my entire career. It's all I've ever done. And for most of that time, it's been a nice, quiet existence. I didn't bother anybody, nobody bothered me, I just quietly got on with my research. And actually, for most of that time, if you'd asked somebody to write a progress report on AI, they could safely have written, well, there is progress, but it's relatively slow. That changed. That seemed to change around about 10 years ago. And as Ramón said, AI now is very much in the press and very much in the public consciousness, and I'm sure that's why many of you came. But at the same time, it's really difficult, even as AI professionals, to really understand what it all means and where it's going. And these advances, which seem impressive, are they really as impressive as they seem? So these are some of the questions that I'm going to address. So in the talk, what I'm going to talk about is what is artificial intelligence first, and Ramón already said this is not an easy question to answer. We're going to talk about how AI researchers actually go about AI. If you want to build an intelligent machine, how exactly are you going to do that? And we're going to see a number of different approaches to AI that have been proposed over the years. And where that's going to take us to is the current thing in artificial intelligence, which again, as Ramón referred to, I call big artificial intelligence. So this is where big artificial intelligence is throwing lots of data and lots of computer power at a problem. But then we'll then talk around the limits of big artificial intelligence, and we'll ask ourselves, can these current approaches really lead to true artificial intelligence? So let's start with what seems like a really easy question to answer. What is artificial intelligence? Now, as an AI researcher, one of the frustrations I have is that everybody has their own opinions about what AI is. You all have your own opinions because you read books, you watch TV shows, and you watch movies. And Hollywood gives us very compelling impressions of artificial intelligence. Some of them are very positive, most of them are not very positive. But you're all left with some idea about what AI is. So, the current Silicon Valley obsession in artificial intelligence is something that we could call general intelligence, artificial general intelligence. So let's call this the Hollywood dream, because it's the picture that Hollywood has given us many times in the movies over the years. The idea that we have machines which are as fully capable as human beings, machines which can do anything that a human being could do. Okay, and without thinking about it, you could mention, I'm sure you could think of movie shows and TVs that you've watched and books that you've read that present you with this idea. I say most of them then go on to explore possible negative consequences of having machines that are as smart or maybe even smarter as humans. And in artificial intelligence, if you really want to irritate an AI researcher, the way that you do this very quickly is to mention The Terminator. It's a great movie. It's a great movie, and I enjoyed it just as much as anybody else enjoys it. But it's science fiction. But there is a plot device in The Terminator, which in AI terms is called the singularity. So let me explain the singularity to you. The idea of the singularity is that at some point in the future, we don't know when, but at some point in the future, machines will be as intelligent as human beings. Now, once we have machines that are intelligent as human beings, they can rewrite their computer code. They can improve their computer code. And at that point, once they've just improved their computer code, even a small amount, we have machines which are smarter than people. And then they can do the same thing again. These smarter machines can improve themselves. And you can see where this goes. And this is exactly, of course, the plot device in the Terminator movies. And that's called the singularity. And some people, some serious people, are worried about the idea of the singularity because they're very concerned about having machines that are smarter than human beings and losing control, because we won't be able to keep up with these machines. So, my position, and I suspect Ramón's position as well, is that actually this is this is actually not what gets us out of bed in the morning. This is not what most AI researchers are trying to do. This is not what Ramon's institute is focused on, I think. We're doing something slightly different. If we're not trying to build general intelligence, machines that are as fully capable as human beings, then what are we doing? We're doing something which is very often called narrow AI. What is narrow AI? The idea of narrow AI is that we look at a task which currently only a human being can do, and we try to get machines to do that very specific task. And I'll give you a couple of examples in a moment. This is narrow AI. Getting machines to do something which currently only human beings can do. But one thing, not trying to build a machine that can do everything. You can do an infinite number of things. You can tie your shoelaces, you can cook an omelette, you can tell a joke, you can do all of those things. In narrow AI, what we do is we just look at one particular task and we try and build a machine that can do that task. Now, the truth is, the overwhelming majority of AI research is focused on this. So let's have a look at some examples of these tasks, some examples of narrow AI. I should say, Ramón already mentioned this point, but again, it's an important point to come back to. The fact that we have a machine that can do something, and potentially do it better than a human being can do, doesn't mean the machine understands what it's doing. We have competence without comprehension. And it's very often easy to convince yourself, and I'll show you some videos in a while to illustrate this point. It's easy to convince yourself that just because you have a machine which can do one thing, which seems to require intelligence in humans, that it must therefore be capable of doing a wide range of other things. Like playing chess, for example. I can play chess. I play chess very, very badly. Machines have been able to beat me in the game of chess since I was about 12 years old. So we associate playing chess with intelligence, and we think if we have a machine which can beat any human being in the game of chess, that must mean that we must be on the verge of broader breakthroughs in AI. That is not the case. We have machines which can do something very competently. That doesn't mean that they're as fully competent as human beings. So let's have a look at a couple of examples of some narrow tasks that we might want machines to do for us. And one is translation. At the turn of the century, 24 years ago, automated translation felt like it was a long way in the future. It felt like something which was a remote prospect. Huge amounts of money over the years have been devoted to automated translation. And you can guess in the 1950s, the big thing was translating from Russian to English. And it's a big thing again, it turns out. But actually, competent automated translation felt like it was a long, long way in the future. And now we routinely have automated translation tools that are used by hundreds of millions of people productively every day. Google Translate is the best known example. There are many others of these. Many people don't realize that that's AI. They just think that's a computer program. Let me tell you, that's classic AI. And one of the really frustrating things for me is that AI delivers what I think is one of the miracles of human technological achievement, and everybody takes it for granted. They don't realize quite what an astonishing thing automated translation is. This is an ancient dream of humanity. This is the Tower of Babel dream, remember? And AI researchers deliver it, and everybody takes it for granted, and they don't even realize it's AI. Now, with Google Translate, you can translate from English to Spanish, from Spanish to Catalan, Catalan to Arabic, Arabic to Russian, and then back to English, and it will do a competent job. Not a perfect job, but a competent job. But it doesn't, in any sense, understand what it's doing. And as it processes the sentence that you're translating, at no point does it understand those sentences in the same way that a human being or a human translator would understand. Let's have another look. Driverless cars. Again, huge, unimaginable amounts of money have been directed at driverless car technology. Since the 1920s, it's that old, is the idea of driverless cars. This century, as it seems like a more plausible idea, again, huge amounts of money have been directed at driverless car technology. It still seems like it's close, but we're not quite there yet. The idea of having a car with no steering wheel whatsoever, still feels like it's a long way off. So what is the big challenge with driverless cars? Well, it's not deciding whether to slow down or speed up or turn left. The challenge in driverless cars is understanding what's around you on the road. Where am I and what's going on around me? Understanding that that's a pedestrian, that that's somebody on a bicycle, and so on. This is where the AI is required to be able to interpret all that information. And that's something that we as human beings, by and large, take for granted. This tells us something else about AI, by the way. A lot of the things that are very difficult for AI are completely trivial for human beings. A lot of the things that are very difficult for AI are completely trivial for human beings. Okay, now, the driverless car technology doesn't have anything to do with the automated translation technology. These are examples of narrow AI. We're building a program which can do one specific thing. So, this is the kind of thing that we want to do in artificial intelligence. How exactly do we do it? Well, here is another conundrum. You might imagine that the starting place for AI is the brain. Right? That the brain is the root of human intelligence, we know that. So you would imagine that maybe what we're trying to do in AI is to recreate brains. Absolutely not. And when I was an undergraduate studying AI 35 years ago, more than 35 years ago, sadly, actually the view was that the brain was too complicated and too messy and too big to be able to try to be the root of artificial intelligence. That we couldn't do that because it was just too hard to understand what the brain was doing. So actually that's not what we're trying to do. It's a common misconception about AI. We're not trying to build artificial brains. Although, as we'll see, that doesn't mean that we don't use some ideas from neuroscience. So, we're going to look at three approaches to artificial intelligence. The first is what's called symbolic AI. The second is machine learning, neural network AI, and deep learning. And the third is the most recent, the idea of big AI. So let's start with symbolic AI. So, if you're not going to use the brain as your starting point for artificial intelligence, what else are you going to do? Well, symbolic AI roughly says that instead of using the brain, what you do is you look at the mind, the conscious mind. When we contemplate courses of action, what we're going to do, we very often have a conversation with ourselves. We have a conversation in language. We weigh up the pros and cons of various different possible courses of action. And we debate those mentally in a conversation with ourselves. And we do that, crucially, in language. Roughly speaking, symbolic AI says that what we do is we try to model those explicit, conscious, linguistic processes. That's why it's called symbolic AI, because language is made up of symbols, the words, the letters, and so on. And we actually model those directly. So, more precisely, the idea of symbolic AI is roughly speaking as follows. Suppose we want to build a machine which can translate from Spanish to English. Symbolic AI says that what we need to do is to find out the knowledge that a human expert translator uses and give that knowledge to the machine. We find out what knowledge a human expert uses and we give that knowledge to a machine. So literally, with symbolic AI, we would go and talk to a human expert translator and we would find out what knowledge they used. How, if you've got a sentence like this, tell us how you would go about translating that. And in particular, what knowledge you use when you translate it, and we then give that knowledge to the machine. So in symbolic AI then, intuitively, the idea is what we're concerned with is modeling the mind, the explicit cognitive reasoning processes that we all seem to use, and that intelligence is a problem of knowledge together with reasoning, to be able to apply that knowledge to particular problems. So the big idea in symbolic AI is that intelligence is primarily a problem of knowledge. Intelligence is a problem of knowledge. That, if there's one slogan for symbolic AI, it would be that slogan. Intelligence is a problem of knowledge. So if we can give a machine suitable knowledge, it will be suitably intelligent. Let's have a look at a famous example of symbolic AI. And one of the reasons this example is famous, and deservedly so, is that it was one of the first computer programs which demonstrated better than human level capability at a problem that was really interesting. And the problem that it was concerned with was diagnosing the causes of blood diseases in humans. So, you imagine that you have a doctor, and the doctor would actually have a conversation with this program. The program was called MySyn, and it would be very much like ChatGPT. The program would ask questions. Does your patient have a fever? Is your patient sleepy? Questions like this. And in the end, it would come up with some kind of diagnosis. I think your patient has Lassa fever with probability 0.6. So how did it do that? The big idea then was to go and to talk to human experts in blood diseases and find out the knowledge that they use. And the way that they coded that was using discrete chunks of human knowledge that are called rules. And this is a very famous rule. This is an actual rule. On the left-hand side, it's in English. And on the right-hand side is the actual computer program code that was used to express that rule. So what this rule does, imagine that a doctor is looking at some organism under a microscope, a bacteria or something like that. And the rule says, if the thing that you're looking at does not stain using the Gram method, so the idea is with this is that some microorganisms, if you put a colored dye on them, they absorb the colored dye, some of them don't. And so this is a diagnostic tool that's used. You can use it to eliminate certain types of organisms. So if it doesn't stain, and it looks like a rod, the morphology is a rod shape, and it's anaerobic, so it doesn't breathe, then there is evidence, 0.6, that means roughly speaking probability 0.6, that the thing that you're looking at is a bacteroid, whatever a bacteroid is. Now, this is the actual rule, this is the actual computer code that was used to express that, and if you squint a bit, you can see how this is roughly capturing the things on the right-hand side. If the thing that you're looking at is gram-negative and the morphology is rod and it's anaerobic, then conclude it's bacteroids with probability 0.6. And MySyn used hundreds of those rules. And the way that they were derived was going and talking to human expert physicians to find out about how they diagnose those. Now you can imagine, immediately, I don't know what you all work at, but for example, if you work in a bank, maybe one of the problems that you've got is identifying people who are going to be a good bet for a loan. So humans do that, you're in a bank, experts do that in a bank, find out the knowledge that they use, and code that knowledge up using rules like this. And this led to a huge wave of innovation in the 1980s, what were called expert systems that did this. And you'll notice this is one very specific problem that's being looked at here. Now, I say the reason that MySyn became so celebrated was that it proved to be better at diagnosing blood diseases than human expert doctors were. So this was a big achievement. Where did this go to? Well, one famous experiment from Doug Leonard, whose picture is on the right, a very charismatic and brilliant AI researcher, sadly passed away last year. But Doug became convinced that actually all of intelligence is a problem of knowledge. All we have to do to get the Hollywood dream of AI, machines that can do anything that a human being could do, is give those machines everything that a human being knows. So he got funding, a lot of funding, for a project called the CSIC project, and they set out to code up using rules that look very much like this. They set out to code up everything that a reasonably educated human being knows. Now just pause and contemplate that for a moment. Everything that a reasonably educated human being knows would have to be explicitly written down in the form of those rules and given to the machine. And at one point, this project, the CSIC project, had rooms full of people busy writing out those little rules to try to code up everything that you know. Well, so let's just some examples of these, all the knowledge that you've used. Red taps produce hot water. The sky is blue if there are no clouds. You can't eat Kansas. This is a famous example. Why do you have to tell it that you can't eat Kansas? Because if you don't tell it, it won't know. You all know that you can't eat Kansas, but the machine doesn't. You'd have to explicitly tell it. Cats are often pets, but not always. Yeah? All of the knowledge that you use every day. And this isn't the kind of thing that you're taught in a classroom. This is just the kind of background knowledge that you pick up as a human being in your life. You learn all this stuff without nobody has to tell you that you can't eat Kansas. You just acquire that knowledge, but you'd have to explicitly give it to the machine. Well, Doug was very optimistic about the future of this project. He thought that within a few years, CSIC would be smart enough that it would be able to write its own rules. It never got anywhere close to that. It's an interesting project. It had successes in its own way, but it was a lot of money spent on something which didn't deliver his very, very ambitious dreams. And it's often cited as an example of AI hubris. And it's often cited as the point at which the symbolic AI dream started to fade. So symbolic AI had successes and still does have successes, these expert systems that I've talked about in particular, but it didn't prove to be a kind of a magic ingredient. Well, if we're not going to build a machine where we explicitly give it all the knowledge that a human being has, how else are we going to do it? Well, there's another idea in artificial intelligence, which is that instead of explicitly giving the machine all the knowledge, what we do is we just show it what we want it to do and let the machine learn. And this is the area of neural AI and machine learning. So let's see a classic example of machine learning. This is called supervised learning, and it's where the machine learns to recognize a human face. And the way that we do this is we provide what's called training data. And the training data comes in the form of an input, in this case, the picture of a human face, together with a desired output. And the desired output is just the name of the person in that picture. So the training data that we give it is a picture of a human face and the name of that person. And what we're doing is we're saying, if I showed you this picture, I would want you to produce this name. If I showed you this picture, I would want you to produce this name, and so on. And we provide, in the training process in machine learning, we provide training data in exactly this form, an input and an output pair. And the idea is that in the end, if we show it a face that it's been trained on, it will be able to produce the output that we would want it to produce. You've just learned an incredibly important lesson about artificial intelligence. And artificial intelligence is nothing without data. And data, very often, is just as valuable as the actual AI programs that are running behind the scenes. And if you're working for some company and you're looking for some insights into how to put AI to work, before you start thinking about an AI strategy for your company, you should ask yourself, what is our data strategy? And one of the big breakthroughs in artificial intelligence this century was building data sets like this, curated, high-quality data sets that could be used for training artificial intelligence programs. So, very well, but how exactly does it work? Here, the technology which has started to work this century is called neural network technology. It's not a new idea, far from it. It goes back to the 1940s and two American researchers, McCulloch and Pitts. And McCulloch and Pitts were struck by the following observation. If you look at a human brain under a microscope, you'll find that it consists of enormous numbers of nerve cells called neurons that are connected to one another in vast networks. And we don't have precise figures, but in a typical human brain, there's something like 85, 86 billion of these neurons. I'm sure in this room, the average is much higher than that. And they're connected in enormous networks, each nerve cell communicating with up to 8,000 different other neighbors. And they're busy communicating. And what each of those individual neurons is doing is a very, very simple pattern recognition task. So let's look at what McCulloch and Pitts thought was, well, these look like electrical circuits. Could we do this with electrical circuits? And the answer they came up with was, in principle, we could, but actually they had no way to build these things. And electrical circuits at the scale of a human brain, just was not remotely plausible in the 1940s. But this idea of reducing a complex problem like recognizing a face down to large numbers of very simple decisions is the idea behind neural networks. And the modern idea is that what we can do is not do it in electrical circuits, but do it in computer code, in software. So let's make this slightly more complicated, slightly more realistic, sorry. So here we've got a very stylized picture of a simple neural network. That's actually a lion. For some reason, it's coming out quite fuzzy. And how would a neural network recognize a picture of a lion? Well, this picture of the lion is made up of millions of colored dots, the pixels that are on your camera. Yeah, the megapixels. These are colored dots that make up that picture, millions of them. So imagine that the neuron in the top left there is looking at the top left pixel, and it's just looking for a particular color, say the color yellow. That's all it's doing. And when it sees the color yellow, it becomes excited and communicates with its neighbors. Now that's a very, very simple task. You can do that with one line of computer code. It's a very, very simple task. Then maybe the next neuron along is seeing all these connections from all these other neurons. Maybe all it's doing is looking to see whether a majority of those connections are active. If it's getting a signal for a majority of those connections. And when it sees that a majority of them are active, it sends out a signal. Now, the point about neural networks is that a complex task like recognizing a picture of a lion can be reduced to a very large number of simple decisions. And the crucial thing that we do when we build a neural network program is we train it, and what that means is we continue, every time we show it the input-output pair, the picture of a lion and the name lion, or the picture of Alan Turing and the name Alan Turing, what we do is we adjust the neural network using some mathematics that we're not going to go into. We adjust the neural network so it's going to produce the answer that we want it to. Now, it turns out that training process to be able to recognize people and to recognize lions requires, it's not difficult, but it requires a lot of data and a lot of computer power. But this is the technology that started to work around about 10, 15 years ago, and this neural network technology is the reason why AI is so fated today, and it's the reason that I'm here, the reason that you're in this room. The key idea of neural networks is that a complex task can be reduced to a very large number of extremely simple tasks, and that we can train an artificial neural network to be able to carry out those tasks for us. So, this is neural network technology. Let's see an example of a program that's trained using a neural network. This came from DeepMind. DeepMind, a UK-based company that's now owned by Google, and one of the world's largest artificial intelligence research outfits. And the following program was released by them in, I think, 2014, maybe the end of 2013. And it's a computer program which trains itself to play Atari video games. And it's got two neural networks, as it happens, that are in there. And basically, as we watch the video, what I want you to bear in mind is the following. It doesn't know what it's doing. It's playing randomly, but every time it gets a point, That's a bit of training data for its neural networks. And basically it says, if I get a point in this game, then in the same situation, I'm going to do the same thing again. So let's roll the video. Okay, so at the beginning, it's pretty useless. It's managed to hit the ball there, but it's missing, doesn't know what it's doing. It's just experimenting. But every time it gets a point, it updates its neural networks. In the same situation, I'm going to do the same thing again. And it just does this repeatedly. So it gets the data just by repeatedly playing. After 400 training episodes you watch, it never misses. Actually kind of boring, right? Never misses. Now you might think that's about as good as it's going to get. Never misses, that's perfect play, right? But then something weird and unexpected happened. Watch what happens on the left-hand side of the screen. It discovers this. Now nobody told that behavior was there. Remember? With symbolic AI, what you would do is you would go and talk to a human expert player and you would say, how do you play this game? And you would give that knowledge to the machine. The program discovered this just by repeatedly playing. And it discovered on its own that this was the quickest way to get a score. This tells you several things about artificial intelligence. One of the things is that actually programs that learn in this way often learn in ways that you don't expect. Yeah? They can often learn behaviors like this, which are not wrong according to the rules of the game, but that we didn't expect. We didn't realize that these behaviors were going to be there. But here is another crucial point. You can't ask the machine, why did you drill a hole through there? Why did you do that? It's got no idea why it's doing it. It's just a neural network that's optimized to do that tiny little task, and it does it very well. But it can't explain to you what its strategy is because it has no idea. That's not the way that this technology works. So we have these programs which are capable of very cute things, but they're not aware of what they're doing in any meaningful sense, and they don't understand what they're doing. So this technology, neural network technology, started to work about 15 years ago, and it unleashed a huge wave of activity around AI. So exactly the same idea that's used to recognize Alan Turing's face can, for example, be used to recognize a tumor on an X-ray scan. Or if you have a Tesla, does anybody in the audience have a Tesla? Nobody's prepared to admit that they have a Tesla. It's fine to own a Tesla. There's nothing wrong with owning a Tesla. But if you own a Tesla, and Tesla, you put your car in self-driving mode, it has to be able to, remember, understand what's on the road. It has to be able to realize that that's a stop sign, that that's a pedestrian, and so on. How does it do that? Exactly that technology that I described. Neural networks trained with probably millions of hours of data where somebody has actually labeled the data, literally labeled it with this is a pedestrian, this is a stop sign, and so on. And you can imagine endless other applications. Again, imagine you're a bank and you want to be able to recognize when people are a good or a bad bet for a bank loan. The training data is previous applications that people have made, and the label is whether or not they defaulted on the loan. And you can immediately see what people would want to do that. I don't recommend doing that, by the way, but you can immediately see that that would be the kind of thing that people would want to do. So the big tech companies, the world's richest companies, trillion-dollar companies, start to see that this technology is working, and they start to see that it's capable of doing interesting things, and they start to invest massively. Now, if you're in Silicon Valley, and you want to get an advantage on your competitors, you could try hiring very clever scientists and hope for the best. But it turns out there's another route with neural networks, which is just build them bigger and throw more data and more compute power. And actually, it turns out that with neural networks, there are what are called scaling laws. And roughly speaking, what these scaling laws say is that the bigger the neural network, the more data, the more computer power you can throw at it, the better it's going to be, the more competent it's going to be. So then we see Silicon Valley starting to scale up the size of their systems. The next generation of our AI model is going to be 10 times bigger. And the generation after that, 10 times bigger. The neural networks are 10 times bigger. The amount of training data that we use is going to be 10 times more, and so on. And that takes us to the current frenzy of big AI. So this is neural networks scaled up with vast amounts of training power and vast amounts of data. And one particular program got people's attention when it was released in June 2020. We were all kind of semi-locked down still in June 2020, actually not semi-locked down, completely locked down. But this program was released by OpenAI, and we had some fairly precise data about its scale. Neural networks had what's called 175 billion parameters. A parameter in a neural network is either an individual neuron or a connection between the neurons. Remember, a human brain has something like 90 billion, 85 to 90 billion individual neurons. We're not far off, just in terms of raw scale, we're not far off the scale of the human brain. And when I studied neural networks in the 1980s, they were massively smaller. I mean, 10 million times smaller than the current ones. And what about the training data? The training data for GPT-3 was 500 billion words. Ordinary human text, but 500 billion words. Where on earth do you get 500 billion words from? Well, you start by downloading the whole of the internet. All of it. Everything that's on the World Wide Web. You go to every web page, you take all the text from that web page, and then you follow all of the links that are in that web page, and you do the same thing again. Every advertising brochure, every bit of government regulation, all of Wikipedia, all of Reddit, everything that's on social media, you grab all of that data and you download it, and you use that data to train your neural networks. And what it does is the GPT-3, it's the canonical example of what's called a large language model, which is a very unhelpful bit of terminology. But actually what large language models do is something ridiculously simple. You see this every time you use your smartphone. So if I open up my smartphone and I start sending a text message to my wife and I type, "I'm going to be," my phone will suggest completions, the next words that appear. And if I type, "I'm going to be," the completions might be late or in the pub or late and in the pub. How does my phone know that? Because it's got some simple machine learning where it's learned that the likeliest next words after "I'm going to be" are either late or in the pub. The training data is just the text messages that I've sent. The more text messages I send, the better it's going to be. Yeah? But all large language models do is exactly the same thing. When you have a conversation with GPT-3 or ChatGPT, you give it a prompt, which is a piece of text, and all of that training data is used simply to try to predict what should come next. What should the next words be after that prompt? So, for example, the prompt might be a one-paragraph summary of the life of Winston Churchill. And I've tried this, and you get an incredibly good one-paragraph summary of the life of Winston Churchill. Why? Because imagine how many summaries of the life of Winston Churchill it's digested, if it's digested everything on the World Wide Web. But here's a crucial thing. It has no idea whether it's telling you the truth. That is not the point of the technology. It's simply trying to make its best guess about what should come next. So one of the early examples that I tried was, "Tell me about Michael Wooldridge." I'm relatively modest, but not that modest. I was curious, what does it know about me? So it came back with a few sentences. Michael Wooldridge is a professor at Oxford, tick, who specializes in artificial intelligence, tick, studied his undergraduate degree at Cambridge. No, I didn't. So we developed the most powerful AI technology in the world, and the first thing it does is insult me. So why would it come out with that? Because it's not trying to tell you the truth. It's trying to make its best guess about what should come there. And it's probably read lots of biographies of Oxford professors, and actually studying at Cambridge is a very common thing. So it fills in the gap. It does this all the time, and it does it in very plausible ways. So that's an important lesson that you need to learn. Anyway, my point here is that all of that training data and these vast neural networks are going into just doing what your smartphone does. The difference is scale, and the scale of these things is astronomical. And by the way, the computer power that's required to do that training, to configure the neural networks, is unimaginable. The current models that are being released, we know that they use something like 60,000 AI supercomputers, each of them costing the order of $100,000, running for months. The current models that are being released, the GPT-4 type models and the models from Meta and so on, we estimate the cost of those as something like $500 million to build one of those models, just because of the scale. It's unimaginable scale. But it does something interesting. So this is, again, a conversation that I had. This is actually a conversation with GPT-3. And this is from a test for machine intelligence that was actually developed in the 1990s. But in the 1990s, there was no AI that you could remotely have applied this test on. And I'm just asking it some common sense questions. These are not advanced reasoning. This is not advanced philosophy or mathematics or anything like that. This is common sense understanding of the world. So I ask it questions like, if Tom is 3 inches taller than Dick, and Dick is 2 inches taller than Harry, then how much taller is Tom than Harry? Tom is 5 inches taller. So green means it got it right, red means it got it wrong. Now my point, the reason I'm using this one is that what it's demonstrating here is what seems to be some understanding of the concept of taller than. So for example, it understands that taller than is an irreflexive concept. Tom cannot be taller than himself. But that wasn't what we trained the model to do. We just gave it a ton of data. So where did that come from? Now, I cannot begin to tell you how many PhD students right now are trying to dig into this to understand exactly what these models have acquired. They've acquired some interesting capabilities, but honestly, we don't know what. And it's a really weird situation. We've got a system which is doing something which appears to be very impressive, but actually we don't understand in a deep sense what it's doing or why or how it acquires that capability. Now, some people believe that all we need to do is just continue this scaling, make it 10 times bigger next time, and it will be 10 times more competent. And that within a couple of iterations, we will have the magic ingredient, that scale is all that we need. Now, actually, as Ramón said in the beginning, I don't believe that's the case. Ramón doesn't believe that's the case. And we'll talk about why in a moment. Let's look at some of the questions, some of the other questions. On a map, which compass direction is usually left? And it says north is usually left. I actually went to look to see whether there were any countries that conventionally put north at the left, and no, I couldn't find it. So why it's getting this wrong? I have no idea why it got this one wrong. Which was invented first, cars, ships, or planes? There's no ambiguity in that question, but it says cars were invented first. I mean, again, go back to the training data. There must have been countless examples of the history of transport where this was why does it get that wrong? Believe me, somebody is working on a PhD on this right now to try to understand that. So they are impressive on one level, but we don't understand exactly what they're doing, and we don't understand the limits of what they're doing. And I'm not going to talk about these in any more detail, but this is just also we have AI that can produce images that also it seems like it's very impressive. The technology is a little bit different, but the idea of using very large amounts of training data to be able to train is the same. But I'm not going to stay with those. So, remember, with symbolic AI, the slogan was, intelligence is primarily a problem of knowledge. The new idea is that intelligence is a problem of data, and that the idea is, give the program enough data, then we will be able to get to artificial intelligence. But let's just pause for a moment and look at what you can do. These are the capabilities. It's an incomplete list, but these are some of the dimensions of intelligence that a human being has. These are all capabilities that you have. The red ones are capabilities in the physical world. The blue ones, roughly speaking, are mental capabilities. So, for example, you can understand natural language. That's what you're doing now. You can understand what somebody is saying. You can solve problems. Recall just means that you can remember things. You can do some simple mathematics, arithmetic. If you have 2 bananas and I give you another banana, you have 3 bananas. You can all do that. You can do some planning and logical reasoning. So all these are all kind of mental capabilities. And then over here, we've got capabilities in the physical world. We can navigate around the world. We can coordinate ourselves with other people. When you all leave the lecture theatre, you'll coordinate yourself so you won't bang into each other. We all do that very naturally. Hand-eye coordination. We can manipulate things. We have dexterity. So what have large language models actually delivered? Well, in truth, not much. They can do natural language processing. They're very good at natural language processing. They can't do anything in the physical world. That's not what the capability is all about. That's not what large language models do. They're to do with language. And they're possible because you can get lots of language by downloading the whole of the World Wide Web. So they can't do anything in the real world, but it turns out, actually, they're not very good at other things. Even very simple problems of arithmetic, they can't do. So, for these reasons, I am skeptical that this current technology, impressive as it is and useful as it is, and there are lots of uses for it, are the end of the road for AI. I don't believe that they're the end of the road for AI. So, let's go on and talk about some other issues related to this. Let's go back to the Hollywood dream for a moment. You remember the dream of artificial intelligence, the idea of general artificial intelligence, the idea of having machines that could do anything that a human being could do. And remember, when we talked about Google Translate, I emphasized that competent as it might be when it does the translation, it doesn't understand in any meaningful sense what it's doing. So let's ask ourselves whether machines can have understanding. And the biggest idea around whether machines could understand comes from Alan Turing. The late, great Alan Turing, one of the greatest minds of the 20th century, he came up with the Turing test. And the Turing test is beautifully simple. What happened was, at the beginning of the 1950s, there was the idea of AI was in the air, even if people didn't really understand what it was going to be all about. And Turing got very fed up with people saying machines will never be able to do X. And so he came up with the Turing test as a way, basically, of stopping these arguments. And the particular idea of the Turing test is it's a test for understanding. So what Turing said is, what we're going to do is we've got an interrogator, person A, who's interrogating something but can't see the thing that he's interrogating or she's interrogating. And he said, it would be via a computer terminal or a teletype, as it was in those days. And you would just have a conversation with it. Again, very like the conversation that you have with ChatGPT. And the goal of person A is to figure out whether the thing on the other end is a machine or another human being. And Turing's key idea was, if you can't tell, after a reasonable amount of time, whether the thing on the other end is indeed a person or a machine, if you can't tell the difference between what a machine's doing and what a human is doing, then stop arguing about it, Turing said, and accept that the thing has some understanding. So, you should accept that the thing being interrogated has human-like intelligence. Doesn't mean it is human intelligence. It's not saying it's the same thing as human intelligence or human understanding, but you can't tell the difference, so there's no point in arguing about it. So the computer is doing something indistinguishable from human intelligence or any understanding by a reasonable test, then stop arguing about it. So this is a Turing test. Now, the Turing test is a fascinating, beautiful thought experiment which actually is not a mainstream challenge for AI these days at all. It just addresses a tiny little dimension of human intelligence. You remember all those different dimensions of intelligence that I put up there? It's really just evaluating one of those, natural language understanding. So it's not really a good test for AI as a whole. But it's still a beautiful thought experiment. And I think it's probably fair to say that at some point in the last couple of years, we quietly passed the Turing test. For all practical intents and purposes, the Turing test was passed. That doesn't mean it's game over for AI, though, because it only evaluates one tiny little narrow aspect of intelligence. But also, there's an important distinction. Suppose that you write a computer program and we run the Turing test, and we can't tell the difference between your program and a human being. So your program passes the Turing test. That isn't the end of the story. And there's a distinction that's made in artificial intelligence between what we call strong AI and weak AI. So here's how it goes. Strong AI is the claim that your program actually understands in the same way that a human being understands. That not only is it passing the Turing test, but actually it understands in the same way that a human being understands. That's the claim of strong AI. Now, if we succeeded with strong AI, then we would have machines which actually experience things understood in exactly the same way that a human being does. The weaker version, what's called weak AI, is the claim, okay, we're not claiming that the machine understands, but it can appear to understand. It can emulate or simulate such understanding. Now, given what I've told you about how ChatGPT and the way work, what do you think ChatGPT is doing? Is it doing strong AI or weak AI? Remember, what it's doing is that prompt completion. Do you think that's understanding in the same way that we understand? Or is it weak AI? Hopefully it's pretty obvious what I think at this point, right? I mean, I think it's a version of weak AI, right? The machine doesn't understand what it's doing, but it can convince us that it looks like it's understanding. And that's a powerful thing to have. That's a useful thing to have. Okay, let's move on. Can machines be conscious? It's another big question. Now, one of the fascinating things about this is that until 3 or 4 years ago, this was a purely philosophical problem. It was discussed by philosophers, but it wasn't of practical relevance in AI. But now we actually have computer programs where serious people claim that they have consciousness. So it becomes an experimental science. So it's an extraordinary time to be an AI researcher. Can machines have consciousness? Well, firstly then, what is consciousness? Well, we don't know. It's one of the big mysteries of science. We know that the gooey mess inside your head somehow leads to you and the experiences that you have, which may at this point be boredom or tiredness or something like that. But it somehow the mass of neurons and so on that are in your brain gives rise to you and all the experiences that you have. But we don't know how it does that. Yeah? And actually, this is what's called the hard problem of consciousness. We know that certain electrochemical processes in the brain give rise to human experience, but we don't know how. But we have some ideas. And one idea is that subjective experience is crucial for consciousness. And subjective experience means being able to experience things from a personal perspective, to actually be able to experience things. So the best known experiment along these lines is due to the American philosopher Thomas Nagel in a very old 50-year-old essay that he wrote called What Is It Like to Be a Bat? And what Nagel said in this essay is that something is conscious if it is like something to be that thing. That is, if you could imagine that thing was having experiences in the world, if you could imagine that this thing was really having experiences. So, something is conscious if it is like something to be that thing. So let's have a look at a few things. So Wooldridge, can you imagine what it's like to be me? Well, at the moment, I'm slightly sweaty and my voice is feeling a little bit hoarse. You can imagine those experiences, right? You can put yourself in my place and you can imagine the experiences that I'm having. So I'm conscious. I have subjective experiences. What about an orangutan? Could you imagine what it would be like to be an orangutan? Put your hand up if you could imagine what it would be like to be an orangutan. Do you think an orangutan has experiences? Orangutan gets hungry, gets bored probably, gets frustrated. It has experiences. What about a dog? Yeah? Do dogs experience things? Do they get angry and frustrated and hungry and bored? I think dogs do, yeah? What about a rat? Does a rat experience things? Could you imagine what it would be like to be a rat? I think yes. What about an earthworm? It's kind of on the border, I think. I mean, I struggle to imagine an earthworm getting bored or frustrated or thinking, I don't want to eat dirt again for dinner tonight. I don't imagine that an earthworm has a... So it's kind of on the border. And what about a toaster? Is it like something to be a toaster? No, of course not. It's an inanimate thing, right? It's not like, doesn't have experiences. Well, is it like something then to be a computer? Well, a computer is just a glorified toaster. It's just an electrical circuit. So the argument goes for the same reason that computers don't experience things. And because they don't experience things, it isn't like something to be a computer. Following Nagel's argument, computers can't be conscious. Yeah? Everybody got me? Yeah? Okay, good. So these are quite advanced concepts of philosophy. So what about a human experience? What kind of experiences do we have? Well, we have two important classes of experiences. The first is the physical world. We experience things in the physical world. We touch something which is hot, it burns us, we experience that. We smell things, we feel things, we experience the physical world. And a lot of growing up is about learning about the physical world, about the world of planet Earth. But we don't just inhabit the physical world, we inhabit the social world. We are great apes, and just as important to our experiences and understanding of the world is not just the fact that if I drop something, learning that it will fall to the ground, but actually learning about the other great apes, the other human beings that are in our world. And human experience is made up of those two types of experiences. One way to explain this is the following. You can ask ChatGPT for an omelette recipe. Yeah, that's what I happen to have for breakfast. Great Spanish omelette for breakfast. You can ask it about an omelette recipe and it will good one. You can ask it to describe the texture of an omelette and it would probably do a great job of describing the texture of an omelette. Has it ever experienced an omelette? No. So again, this is an argument that programs like ChatGPT, because they've never experienced anything in the physical world, that they don't actually have anything like conscious experience. To us, the word omelette is not just a word. It's just a word for ChatGPT, but for us, an omelette means something. And what it means is all the experiences that we've had with an omelette. Yeah, like the great omelette I had for breakfast this morning, the really bad one I had in Paris last year, and so on. That's the meaning there. The experience is grounded in our experiences in the physical world. And GPT has nothing to ground its experience in. It's never experienced anything. You can see where this argument is going. This is an argument against the idea that GPT-type programs have consciousness. And then there's something I want to finally leave you with, because I just think this is fascinating. This is from a colleague in Oxford called Robin Dunbar. And Dunbar is an evolutionary psychologist. And he became fascinated by the following question. Why do human beings have such big brains? Now, we know that we separated from our closest great ape relatives, chimpanzees, orangutans, and the like, I think 18 million years ago, I'm not an expert in this. We know that we separated from them, but we know that their brains are substantially smaller, so why did we get such big brains? And these are expensive in evolutionary terms. It requires a lot of energy to feed a human brain, so they must have delivered something for us. So what exactly did they deliver? And Dunbar's idea was that human beings developed big brains to be able to handle lots of social relationships, big social groups. And what he did, and I think this is one of these pieces of research that I think I wish I'd done this. This is such a beautiful piece of research. What he did is he went and looked to other relatives of ours, the chimpanzees, orangutans, and so on, down to smaller monkeys, and we know what their average brain size is, and we know what their average social group size is. So how many chimpanzees hang around together in the wild? That's the social group size. And you can plot, and it turns out you get a correlation. Now, we also know the average human brain size. So then the question Dunbar asked is, what does that tell us about human social group size? So the prediction is what's called Dunbar's number. Basically, the claim is that brain size, or more specifically neocortex size, correlates with your social group size. That's the factor that determines how big the brains of these animals are. It's how many social relationships they have to handle. So it turns out Dunbar's number, the prediction that this makes about social group size is 150. So what Dunbar's number says is that humans, we have big brains to be able to manage social relationships, close social relationships, with around about 150 other human beings. And what that means is, to be able to handle those relationships means to me to know what Ramón thinks about Carlos, or what Ramón wants Geordie to be able to do, to be able to handle that kind of reasoning. And Dunbar's hypothesis is that humans developed those big brains simply to be able to handle that many social relationships. Why would they have evolved that capability? Well, one theory is that we used to live in the trees. Climatic changes forced us out onto the open plains. That made it possible for animals to prey on us, and an evolutionary response to that is to develop big social groups. And to handle those big social groups, we needed bigger brains, so we evolved bigger brains. That's a theory. That's not rooted in fact. But what Dunbar then did is went to look for evidence of his number throughout human history. And it turns out, time and time again, this comes up. This is the average size of a Neolithic village, for example. Throughout history, it's the average size of a typical fighting group. A centurion, the centurion group in ancient Rome, together with their followers and so on, is around about 150 people. And so there's repeated evidence that this number arises time and time again. So what's this got to do with AI? I think it's the fascinating thing about it is that what it tells us is our big brains evolved so that we can be social. That human intelligence, the thing that distinguishes us from our relatives, our animal relatives, is the ability to handle these large social relationships. But that human intelligence is intrinsically social. Now, that's a hypothesis. It's not a fact, it's a hypothesis, but I think it's an incredibly important fact. I need a big brain to be able to understand what Steve believes about, what Mike believes about Brian, sorry, that's not brain, what Brian wants. So the social brain hypothesis is that human intelligence is connected to our status as social animals. And the social mind hypothesis is that the ability to have conscious experiences derives from the need to see ourselves in a society of other people. I need to understand what Ramón thinks about me. That leads to conscious experiences. So summing up, AI has made real and genuine progress. That, I think there's no question. We now have computer programs that can recognize tumors on X-ray scans, that can recognize human faces, that can automatically translate from one language to another, and so on, that can do these many things, and that's incredible and powerful. And more recently, we have these big AI programs where the idea is that intelligence is primarily a problem of data. But for the reasons that I've explained, I don't think that takes us to the end of the road for AI. Because despite their impressive capabilities, and they are impressive, there are a huge swathe of human capabilities that they don't have. And so there are some ingredients that we don't have yet for general intelligence. And we don't yet know what those things are. Okay, at this point, I think I'm about done. So thank you for your attention. I hope that you learned something interesting and useful, and failing that, I hope I just didn't bore you. Thank you.
Thanks very much, Mike, for this enlightening talk. You are just a bit, not much, a bit late. So what I go straight ahead to the audience to ask questions. I will refrain of asking my own questions to give you more opportunities to give.
Hay una pregunta allí. Espere el micrófono, por favor. Una charla impresionante. ¿Cuál es su opinión en cuanto a las dimensiones del cerebro y las estructuras de las proteínas? Hay muchas personas en el campo que preguntan qué estudios se pueden hacer. Lo siento. Y, por ejemplo, en el mismo sentido, con ChatGPT ya se ha demostrado que influye el cómo utilizamos el lenguaje y las palabras que utilizamos. ¿Piensa que la IA nos hace más tontos y que ya no podemos progresar más? Yo creo que mi respuesta estándar es que puedo recordar en los años 70, cuando las calculadoras estaban disponibles y había un pánico moral sobre que las calculadoras de bolsillo pensaban que dentro de unas generaciones nadie iba a poder hacer cálculos nunca más. La idea es que lo que estas calculadoras hicieron es liberarnos de la carga cognitiva aburrida, que la mayor parte de nosotros encontramos aburrida y llena de errores, y centrarnos más en las cosas que realmente requerían inteligencia humana. Yo supongo, y soy optimista al respecto, algunas personas estarán en desacuerdo, pero yo supongo que la IA, con la IA pasará lo mismo. En vez de hacernos más tontos, de hecho, nos hará más inteligentes. Nos va a permitir tomar mejores decisiones y más informadas en nuestras vidas para poder manejar nuestras vidas mejor. Y es un ejemplo, como un ejemplo es la tecnología wearable, como por ejemplo, yo llevo este reloj Apple, y esto es más como un producto de primera generación. Imaginen lo que esto va a ser dentro de 30 años, sintiendo de forma continua mi fisiología y el estado de mi salud. Y va a monitorizar mi salud 24 horas al día. Y esto acoplado con la IA va a permitirme tomar decisiones mucho mejores sobre cómo llevar mi vida, mucho más decisiones informadas sobre cómo llevar una vida saludable. Imaginen un Apple Watch, te das cuenta de lo estresados que estás hoy, tienes que tomar una pausa, este tipo de cosas. Yo creo, por lo tanto, pienso que la IA es una especie de prótesis cognitiva, algo que nos va a hacer más inteligentes en vez de más tontos. Creo que hay alguna pregunta en la parte de atrás. Hola, le felicito. ¿Está de acuerdo en que el sentido común es el sentido común es la forma más básica de inteligencia que hay? No hemos estado entrenados, no tenemos ningún conocimiento específico, simplemente sabemos cómo comportarnos. ¿Diría usted que el deep learning, la inteligencia artificial, van a llegar a ese punto de tener sentido común? Es una pregunta buena, pero estoy en desacuerdo de que no hace falta aprenderlo. Yo tengo niños adolescentes y si comparo su estado de sentido común y de hace unos años a donde están ahora, puedo ver una gran diferencia. Y es porque literalmente han aprendido sobre el mundo y seguimos haciéndolo todo el tiempo. Por ejemplo, se sabe que los seres humanos, el ser humano típicamente normal, desarrollan una teoría completa de mente, una mente completa cuando son adolescentes, pero lo tienen que aprender a través de sus interacciones con los demás. Tienen que aprender lo que molesta a los demás y empoderar a las personas. Yo creo que sí que es algo que hay que aprender, no es algo que nos lo dan así por gratuito, pero yo pienso que es más probable que lo que la evolución está dándonos no es que alguien haya nacido con esta forma de comprender, pero alguien ha nacido con la capacidad de adquirir esta comprensión. Yo creo que para mí esto es más probable. Sí, yo pienso que va a ser importante absolutamente si vamos a tener ordenadores que puedan comprender cuándo nos van a irritar, que será una cosa bastante útil para el ordenador que lo entienda, que se requerirá sentido común para hacerlo, etcétera. Todo esto hay que la extensión hasta en que los LLMs requieran sentido común y comprensión no se sabe todavía. Se saben con trocitos, pero no todo. Me gustaría añadir una información al respecto. En este campo del desarrollo cognitivo, el trabajo de Jean Piaget y de su escuela nos muestra muy bien lo que Michael ha mencionado sobre cómo desde el principio, prácticamente a la de unos pocos meses, los niños estudió muy conscientemente cómo van aprendiendo y cómo cada vez comprenden más sobre el mundo. Por lo tanto, claramente sí que hay un proceso de aprendizaje a lo largo del camino. Había una pregunta. Hay dos ahí. Una. Gracias. Muchas gracias por su conocimiento que ha compartido con nosotros. Mi pregunta, usted ha hablado sobre las relaciones sociales humanas. ¿No piensa usted que a lo mejor dentro de unos años no estamos creando ahora mismo datos sobre experiencias sociales y a lo mejor dentro de algunos años vamos a poder recoger todos estos datos y entrenar utilizando el concepto de la gran IA, de que ahora estamos entrenándoles con datos de la web? Yo creo que es plausible. Yo tengo colegas serios que piensan que una forma en que esto puede avanzar o ir son datos sobre los seres humanos que son tan importantes, que de hecho lo que la gente va a hacer es básicamente estar siendo monitorizados por la IA y sus datos recogidos, cosechados de sus experiencias, sus emociones, etcétera, cosechadas, por así decirlo, o todos para entrenar a la IA en el futuro. De momento no hemos llegado a este punto, pero no es ninguna idea loca. No estamos demasiado lejos de ese tipo de cosas. De una forma ya, la gente que ya está de acuerdo con estar conectados a los relojes Apple para que están monitorizados para ofrecer datos para las compañías de seguros, ya existe. Creo que es totalmente plausible. Y hay también algunos obstáculos que habrá que superar para que esto funcione. También he oído la sugerencia, dicho sea de paso, ¿por qué no simplemente entrenamos a la IA sobre películas y shows de televisión donde las relaciones humanas, etcétera, están ahí? Podemos aprender de las relaciones a partir de los vídeos y de las películas. No creo que sea una idea tan buena. Hay otra pregunta allí. Puede que ya vaya a ser la última. Dos, entonces. Mi pregunta tiene que ver con el impacto social de la inteligencia artificial. Estoy pensando en un tema específico en los Estados Unidos, de donde yo vengo. Tiene que ver con la escolarización en la casa, en el hogar. Mi comprensión es la interacción social para el aprendizaje. Hay personas que piensan, no, yo puedo enseñar a mis niños en casa porque tengo acceso a... Creo que la educación va a ser una de las aplicaciones más importantes. Yo creo que hay muchas personas que piensan que ChatGPT parece que sea tan fantástico, podemos estar ahí y decir que funcione. Yo creo que es un gran error. Yo creo que muchos profesores humanos comprenden que los niños se les pueden enseñar las estrategias que funcionan para ellos, para la educación, comprender sobre las circunstancias en sus casas y hacer a medida su enseñanza de forma adecuada. La IA no está ahí para hacerlo de forma... La educación por parte de humanos es una de las aptitudes humanas mejores que están por ahí. Yo creo que desde luego va a haber será un añadido, pero la idea de que solamente se le va a poder dar todo a ChatGPT o algún equivalente, creo que esto no es probable de momento para nada. Quiere decir que no sea útil ni una herramienta poderosa, pero la idea de que sustituya a los profesores humanos me parece a mí no posible, no plausible por el momento. La última. Sí, ¿no? Profesor Wooldridge, muchas gracias por su conferencia. Usted habló sobre los límites de este tipo de investigación, pero quisiera que usted me diga otros límites del mundo real. En primero, advertencias sobre las compañías de IA que se quedan sin datos, están creando sus propios datos artificiales. ¿Y cuáles son las consecuencias de ello? En segundo lugar, las empresas de IA van a consumir 10 veces la energía eléctrica dentro de 2 años, la energía eléctrica que tenemos hoy. No hay ningún país que sea capaz de producir tal infraestructura. Entonces, ¿cuáles serán las consecuencias de estos límites? Pregunta muy importante y muy ampliamente discutidas, además. Una preocupación que tiene la gente es que lo siguiente parece bastante probable. Dentro de una década, la mayoría abrumadora en Internet prácticamente va a ser producido por la IA. Esto empieza a verse ya de forma bastante inevitable. Si no es una década, pues dentro de 2 décadas todo estará en Internet. Va a ser producido por la IA. ¿En qué punto la IA va a estar entrenada en contenido producido por IA? Toda la evidencia que tenemos por el momento es que cuando se hace, la calidad de la inteligencia artificial rápidamente decae. Esto es una preocupación de verdad, de que hecho la inteligencia artificial envenene los datos, porque Internet está lleno de contenido de IA que no es bueno para que se entrene la IA. Queremos datos humanos para que se entrene la IA. Esta es una preocupación. En lo que se refiere a los requisitos de energía, es difícil ver esta escalada de más de 1 o 2 generaciones. Si ya gastamos $500 millones para enseñar un modelo de IA con las implicaciones que tiene para la producción de CO2 y consumo de electricidad, ¿cuántas más iteraciones se pueden hacer? Si lo escalamos 10 veces, ¿hasta cuándo podemos hacerlo? Incluso las compañías importantes del mundo no pueden hacer esto más que 1 o 2 más iteraciones. Por lo tanto, al llegar a ese punto habrá que empezar a mejorar la tecnología. No se puede basarnos en simplemente hacer más grande o más grande, más grande. Habrá que hacer una inteligencia artificial mejor y eso es mucho más difícil de hacer. Muchísimas gracias de nuevo. Vamos a agradecer una vez más a Mike por esta fantástica charla. Muchas gracias.
And thanks to all of you for coming.